This is Dr. Indradeep Kumar, Assistant Professor, IARE, Hyderabad. So in this video, we will see energy method, with how to solve the energy by using the energy method. So first we will see introduction to energy principle, and then we will see the Castigliano's theorem. Okay, so first introduction to energy principle. The elasticity method of structural analysis. Just see here the word elasticity method means where we can use the elastic property like Hooke's stress, right? Hooke's law, right? Stress is directly proportional to strain. That is valid for elastic material only. So the elasticity method is for the elastic material only of the structural analysis entails determining stresses and or displacements, which either we can find a stress or displacement or simultaneously both using equation of equilibrium. Means what we have to do, we have to use the equation of equilibrium and compatibility in conjunction with the relevant force in the here. And compatibility means that should be compatible with the, by combining, conjunction is what, by combining with the relevant force displacement or stress strain relationship. Means either it should be the force, when we will apply the force, displacement will be there. When we will apply the stress, then a strain will be there. So force, displacement or stress strain relationship by combining this. The use of energy method is a powerful alternative but equally fundamental approach. So by using the energy method, instead of using directly force displacement or by using stress strain energy, we can go for the another method, that is energy method. That is also equally same approach is there and the better than the these steps. So powerful alternative. While these provides exact solution to many structural problems, they are most useful in providing rapid approximate solution to problem for which exact solution does not exist. Means by normal method, whatever the solution we cannot find or which solution is not available, by the energy method we can get that solution also and even exact also. So that's why this provides, means energy method provides exact solution to many structural problems. So wherever the structural problems are there, by the energy method we can get the exact solution, which is not possible by the normal method or stress strain or force displacement method. Or you can say whose solution is not exist, that also we can find by the energy method. Furthermore, many structures that are statically indeterminate. So that's here, for even statically indeterminate also we can find. Later we will see if indeterminate is there, then one method is called that flexibility method. Right. So in that flexibility method, one option is there in energy method only. So we can remove the members from indeterminate structure to make it determinate, and then we can find easily. So even that's why it's there, whatever the solution is not there. Suppose some indeterminate structure is there whose solution is not available, then what we will do, we will go with the flexible method. And in flexible method, what is that? Just remove the members till that structure becomes determinate. Now determinate is there, we can find the solution. So that's why by using the energy method, any type of structural problem we can solve. So that are statically indeterminate, that is they cannot be analyzed solely using equation of statical equilibrium. So just see that it is the indeterminate structure with the equilibrium equation, we cannot, only with the equation of equilibrium we cannot find. Can be conveniently analyzed using energy method approach, but by the using energy method we can find the indeterminate structure solution also. Energy methods provide relatively simple solution to the deflection problem that are not easily solved by more basic methods. Whatever the basic methods are there, like earlier it's mentioned, though that with that method we cannot find, by energy method we can find also that solution of deflection problem. Energy methods are applicable to a wide range of structural problem and can even be used to form equation of equilibrium indirectly. So energy method are applicable to what? A wide range of structural problem. That's why just now we had seen that even for indeterminate structure also we can find. And if for indeterminate structure, what is that? We cannot find with the equilibrium equation, means the other equation is required. So just here that is there. Can be used to form equation of equilibrium indirectly. So directly wherever we cannot find the equation of equilibrium, in case of energy method, we can go for the indirectly equilibrium equation and then we can find that one. So hence we can say with the energy method we can find for almost every type of structural problem solution, whatever is not possible with the basic method. This module will focus on the solution of deflection problem and the analysis of a statically indeterminate structure. So this chapter is for what? How to find the deflection, right? Our deflection related problem and the analysis of a statically indeterminate structure. Means we will see how statically indeterminate structure can also be solved by using the energy method that we will see in the problems. Okay, so now just see us. We will also include some methods that are limited to linear system solutions. So linear system. What is the meaning of linear? Suppose like y equals to mx plus c. So this is a linear equation or equation of a straight line, right? Means, or if this c is constant or 0, means y-intercept is 0, then we can say directly y is equals to mx, where m is the slope. So now we can say y is directly proportional to x. So if this is the means y will increase, x will increase, right? For that type of system, we can find easily. So we will also include some methods that are limited to linear system. Is whatever the solution is there or method in which this only by this method only can be solved, even that also we can include in the energy method. And that method is called as what? The unit load method and the principle of superposition and the reciprocal theorem. So by these methods, whatever we cannot solve by this, that we can solve. Okay, so figure A depicts a structural member. Here we will see. So just say this is a structural member where load is acting P. So up to this was the original one. This is the original structure. So after applying the load, now this will shifted here. So this much elongation is there by distance y. Okay. So figure A depicts a structural member under a steadily increasing load P. Steadily increasing. It's increasing but with constantly. The load P does work as the member extends. So what happens? Just see here that extension is there, right? Here. So from here, it's extended to till here. So its extension is there. And the law of conservation of energy applied. So now just after member is extending and hence apply the law of conservation of energy. Okay. This work is stored as strain energy in the member. So law of conservation of energy is what? One form of energy converted to another form. Means here we are applying the force, means we are doing the work. Where that work goes, that work is stored in the form of strain energy in that member, and because of that only this got stressed or strained. Okay, so that energy is stored in this part. Because of that only it's got increased from the conservation of energy. Figure B depicts typical load deflection curve for a member with non-linear elastic property. So non-linear elastic. So just see the figure B here. So this is the member that is non-linear, right? That's why this curve is there. Okay. The strain energy U generated by a load P and the corresponding extension Y is then calculated. So now find what U, how much energy is there, and we know that area under the curves gives the total work done. Work done is stored in the form of energy. So U equals to 0 to Y P dy. So strain energy U is P into dy. Or just see here. In this curve, if you will see, just see here in this curve. For first, this we are finding that inner part like this one. Okay. So for this part, means here is the rectangular strip what we are taking here, having the length what? Delta y, right? And this is the P. So wherever it will take means P for this one and into delta y. So this will be energy stored in this strip. That will be how much? P into delta y or dy. Okay. So once we will integrate from where to where, this, okay, 0 to y, then we will get from here to till here whatever the energy will store means inside this one. Right? So now let's see here once again. For a strain energy, what we have taken? Just a small elemental strip of length y. What is here? That can be from where? Here to up to this anywhere. So means P will be there. So this is the length, you can say that as P, and this is y. So for this small elemental strip, what will be the strain energy? That P into dy or del y. Del y here we use, so del y. From where to where are we? Suppose if we will take here, then from here to here. But up to what distance? Up to y distance we are considering, right? So 0 to y means 0 to y. So this will be equals to strain energy. So equals to, because it's energy, so modulus form, modulus of 0 to y, p dy. That is the strain energy equation. Okay. Now area OBD under the load deflection curve. So area OBD, which area? This area. Just now we found, right? Up to this one. So this area is area OBD. Now what about the opposite area? So if this is the strain energy, right, then opposite will be what? The complementary energy. That you know the sum of these two should be energy and complementary energy, like theta is there, or A plus B is 90 degree, then A 90 minus A is B. So then we can say complementary energy or complementary angle of A or complementary of A is B. So whatever is there total minus this, if we subtract, the remaining will be the complementary energy C. So OBD will be the strain energy and OBA will be the complementary energy, and complementary energy is denoted by C. Right. So now just see for this one. Now this time just see here. For this its a pressure is varying. So here we are taking a small elemental strip of delta P, and where it will goes up to this maximum, that Y. Right. This will go up to maximum, this one. So what happened in this case? This will be Y into del P. Right. From where to where? 0 to P. So integral of 0 to P. Right. So C equals to 0 to P Y dP. That is the complementary energy. Okay. So just here, this figure 1 shows what? A strain energy of a member subjected to simple tension, and this is what? Load deflection curve for a non-linear elastic member. So this is curve, that's why. And earlier what we are saying, if it's a linear, then y equals to mx, right? For that, curve will be a straight line. But here this is non-linear, that's why it's curved one. Okay. In contrast to the strain energy, complementary energy is purely a mathematical quantity with no physical meaning. So complementary energy, what? Just mathematical, like 90 minus A or 90 minus B is the complementary of it. So it's just mathematical. There is no significance, or we cannot directly say some complementary energy is there, right? So in a strain energy, whatever the remaining is there, that is the complementary energy. So that's why complementary energy is purely a mathematical quantity with no physical meaning. Means there is no physical meaning of complementary energy, only because of that mathematics. Okay, we are saying that strain energy is there, means the remaining will be the complementary energy. However, it is possible to demonstrate that complementary energy obeys the law of conservation of energy in the type of situation that typically occurs in engineering structures, thereby validating its use as an energy method. So, but what happened? It is possible to demonstrate that complementary energy obeys the law of conservation. Means complementary energy also obeys the law of conservation of energy in the type of situation that typically occurs in engineering structure. So whatever engineering structure, because of that failure, like a stress will act there, that will be, so the law of conservation of energy means one energy will convert it to other. That's why in a structure we had seen what we did the work done, that is stored as a energy. So that follows the conservation of energy, and that only helps us to use the complementary energy method, because it's obeying the law of conservation of energy. If it's not obeying the law of conservation of energy, then we cannot get the exact solution. And already we had seen that even for whatever solution is not possible by the null method, we can go with the by energy method, we can get the solution and even more exact. So because of this, right? If it's not following, means what? Whatever the energies will be there, that will convert one to other one. So we will get the exact energy. There is no loss of energy, and hence whatever either work or deflection is there, in that there is no difference will be there, that we will get the exact value. They are validating its use as an energy method, and hence that we can use as an energy method. Equation 1 and 2. One was for the strain energy, right? Here the strain energy, and 2 is for what? Complementary energy. So equation 1 and 2 are differentiated with respect to y and p. So equation 1 differentiate with respect to y. So just here. Okay. So what we can write this as du, let's see here, dy dy equals to p, or like p. So after integrating, what you will get? So let's integrate here, or integrate. So first u equals to 0 to y p dy. So p is constant out of integral dy, integration from where to where? 0 to y. So that we will get py. So what we have, u equals to py. Now differentiate this one with respect to y. So what we will get, du by dy equals to p. Right, that is here, du by dy equals to p. Now next, what was c? C equals to integral of 0 to py dp. Integrate, y is constant, so out of integral, right? 0 to p dp. Integral of dp is p, so this will be y into p. C equals to y into p. So now differentiate c. So dc by dp equals to what? Y is constant here, so p will be 1. So dc by dp equals to y. So dc by dp equals to y. Okay. Now let's see why we differentiated, that we will see in next slide. Okay. Suppose that the curve of 1b figure, like this curve, okay, is represented by the function where the coefficient b and exponent n are constant. So now what we are taking this as taking what if p equals to by to the power n, some arbitrary type, that may be power n. If suppose this is n equals to 1, right, then this will be p equals to by, right, means it's a linear equation. If n is 2, then p equals to by to the power 2, means now this becomes the parabolic, p equals to by cubic. Like that, whatever we will change the value of n, according to that we will get the curve that non-linear. For only n equals to 1, same becomes linear, right? So for this an arbitrary curve, either it's a parabolic, cubic, or any one that we don't know, so simply we are taking what? P equals to by to the power n. Okay, so now with that we will find this one. Okay, so p equals to by to the power n is there, right? Differentiate this one. So after differentiating this, what happened? Just see here, p by to the power n is there, p equals to, after differentiating, what we will get? dp equals to, b is constant, b, and differentiation of n into y to the power n minus 1. So this will be the dp. This we can submit there, here. Okay, that. So let's see, later we will use this one. So now this is dp, here it is. Okay, now from this, from here again, what is that? P equals to by to the power n. So what can we write this as? P. So can we write this as P by b equals to y to the power n? So from here, p by b power 1 by n equals to y. Let's see, y equals to p by b power 1 by y. Now differentiate this with, okay. So this is, so after differentiating, what we will get? Power 1 by n is there, so 1 by n into p by b power 1 by n minus 1 equals to dp. So that is here, dy equals to, sorry, dy differentiation, so y. dy equals to 1 by n p by b to the power 1 by n minus 1. Right. Now we have the dy, we have the dp. Substitute in energy equation. So what is energy equation? Here. So now we have dy and here dp. So substitute in these two equations. Okay. So after substituting in u, 0 to y, p dy. So p dy is what? This one. So p into 1 by n, p by b power 1 by n minus 1. Right. After taking this one. Put in c. Right. C is what? 0 to p y dp. So y into dp. What is dp? Here. So see, 0 to p, okay, y, and dp is n into b y to the power n minus 1 into dy, right? So this one, 0 to p y into n into b into y power n by y. I wrote just y power n minus 1 is this one, n into dy. So this get cancelled. What is there? Nb is constant, right? So Nb I'm taking out. Nb 0 to p. What we will get? Here, right? Y to the power n dy. Or you can just put here this n b power b y power n. So b power n is what? P, right? So p dy. Just after removing that one. So n into b y power n dy. So from here what you will get? C equals to what? P dy. So here du by dy equals to P, and du by dp equals to 1 by n into p by b power 1 by n, and p, what is that? Here this is what? Just see here y. So p by b power 1 by n is y. So after putting 1 by n into y, so du by dy is p, and du by dp is what? Du by dp is 1 by n y. Okay, so now these two we got. So now for the linear one, same we have seen here just the general equation, and I told you like p equals to by to the power n, depending upon the value of n. If n is 1, then it's a linear. If n is 2, then it's a quadratic, and 3 cubic, right? So now from here, one scientist found, that is the Castigliano, name was there, he found the same thing for the linear only. Means what? Wherever n is there, he substituted 1, right? So now just see in this substitute, well, so what we will get? P equals to by. Then dp will be what? N, so that 1, y per 0, so dp equals to n. So after putting here du by dp, just here, dc by dp is y, and dc by dy is b, that equals to b n into y power n. So n y power n, b y power n is what? That is p. So n p. So dc by dp is y, and dc by dy is n p. So from here, just see the two equations, right? Du by dy is p, and du by dp is 1 n by n into y. So just here, du by dy, right? And du by dy is y, and here what is y? Here that y by n, right? Du by dp. So we can say n du by dp is y, right? So du by dy, and dc by dy is what? P, if n is equals to 1, right? In this equation, if you will put n equals to 1, then what happened? This will be simply p. So dc by dy equals to p, and that is here equals to du by dy. So can we say that if du by dy is p and dc by dy, right? Dc by dy is also p, then du by dy equals to dc by dy equals to p. So that is here, du by dy equals to dc by dy equals to p. But remember, for n equals to 1 only, this way is valid for n equals to 1 only, because here n term is there, right? If n is 2, then we cannot use that one, then it will be 2p. Okay. Similarly, du by dp is what? Du by dp is 1 by n. So if we will put here 1 by 1, that also is 1, so 1. So means du by dp is y, and here dc by dp is what? That also is y. So du by dp equals to dc by dp equals to y, right? So this equation that for strain energy and complementary energy is called as the Castigliano theorem for n equals to 1. This what? Energy method, this is for general one, right? And for a special case, so Castigliano theorem is the special case of the energy method, in that power that p equals to by to the power n is there, where n is equals to 1. Means in p equals to, or Castigliano theorem is defined for only the linear material, that material which follows a linear property, right? Y equals to mx type or P equals to by type. This power should be n. So according to Castigliano, this curve will be the straight line. So this part is what? The strain energy, and this is what? The complementary energy. And sum of these two will be the total. So U is there, whatever will be the opposite remaining, that will be the C. So the CO. Again same. So OBD will give you what? Strain energy for linear. Remember here this curve is linear, that a straight line is passing through, origin is having y-intercept 0 or this p-intercept 0. Okay. So and the opposite is C. So the load deflection curve for a linearly elastic member. So just here this word is important. For linearly elastic member only we can say with when it's following the linear equation. Clearly area OBD is what? U, strain energy, and is equals to the area OBAC. So that's why here we are getting, earlier in previous case du by dy was not equals to dc by dy, or just see here du by dy is P, right? And dc by dy, sorry, dc by dp is y, not dc by dy, dc by dp is y, and here du by dy is P, right? And du by dp is 1 by n y. Okay, so here that must be same, but in this case this will be equals to this one, but in other cases that is not necessary if both, that U will be equals to C. But according to Castigliano theorem, strain energy is equals to the complementary energy. So this is, if suppose they ask to prove the Castigliano theorem, you have to do the same thing right from the beginning, and in last, for Castigliano theorem is valid for the only linear elastic member, hence Bp equals to by to the power n is equals to 1. Means Castigliano theorem is valid for linear, that is n equals to 1, and just put n equals to 1 in the last two equation, right? Du and dc equation, and then just find this one. So now you can see du by dy is equals to dc by dy. So just see here, with respect to y only we are differentiating, u also with respect to y and c also with respect to y, that gives what? P. Now u with respect to p and c with respect to p gives y. This what we have, u du equals to p dy, right? Now take this as, so du by dy equals to p. If in both the cases it's valid, then we can say it's a Castigliano theorem, or C equals to P dy, dc equals to, so dc by dy equals to P. When these things are same, means both is must equals to the applied force, that P, then it's a Castigliano theorem. If it is not equal, then it's not Castigliano theorem. Remember, so Castigliano theorem means still here you have to derive, and then you have to mention what? Du by dy, okay, is equals to dc by dy is equals to P. When means strain energy with respect to y if you will differentiate, and complementary energy with respect to y you will differentiate, both will be same, and that is equals to P. Similarly, strain energy with respect to P and strain complementary energy with respect to P, if you will differentiate, both will be same, and that is equals to y, then it's a Castigliano theorem. So just yeah, this equation is in the form of what is commonly known as Castigliano theorem, in which the differential of the strain energy U of a structure with respect to a load is equated to the deflection of the load, right? So here, so du by dp is deflection, and with deflection it's a load, right? So just here, with respect to a load, so in which the differential equation of a strain energy of a structure with respect to load is equated to deflection of the load. So with respect to load, deflection of the load. With respect to deflection, load. Okay, so that is the Castigliano theorem. Okay, so just see quickly once again. Right, I'm just starting from here, not the theory parts. So from this figure, here again just see here, this part is the extended part because of the steadily applied load. So some energy will be stored. Miss we are applying the load, so some work done is there. So where that work done goes. So by the principle of conservation of energy, work done must be whatever is their form only change, that conservation energy that should not be lost. So where that energy goes, that energy is stored in the form of strain energy here, and because of that only it's got strained. Right. So now if you will see the curve, right, load versus deflection. So here this is the non-linear elastic material, which is a curve. Right. In that, what happened? GOBD and OBA. So OBD we just considered as a what? Strain energy, and OBA is the complementary energy. Now what we did? Here we have taken that one strip for strain energy here. So this strip from where to where it will be 0 to Y it will move. And here in this case P remains constant because up to this total we have to take. So this in this one. So strain energy what you will get? U equals to integral of from where? 0 to Y. So 0 to Y, and P, this Y is varying, right? So P dy. So this will be the strain energy. Now come to this side, that upper part. Right. Here delta P, this side P is varying and Y is constant. So that is called complementary energy. So C is equals to what? From 0 to P. So 0 to P, and here this Y is constant. Right. This Y is constant. So Y into dP. So this is called the complementary energy equation. Right. That is these two equations is here. Next, what we are assuming, suppose the about that curve is varying according to P equals to by to the power n, any arbitrary equation. Now later we will see by putting the value of n. Right. So P equals to by to the power n. Differentiate first P with respect to y. Right. Or just first differentiate this one. So after differentiating P, what we will get? dP equals to nb y to the power n minus 1 dy. Okay. So first, and from here, what will be the y? Y will be equals to P. Y equals to P by B power 1 by n. So y equals to P by B power 1 by n. Right. So now what we have y, right? Differentiate this one. So after differentiating y equals to 1 by n into P by B power 1 by n minus 1 into dP. Now just dP is there, dy is there. Put here. After differentiating this here. So now just see here. U equals to, right, strain energy equation. Here. P dy and y dP. So put here dP and dy. So after putting in energy equation 0 to y, P dy is 1 by n, just substituting that one. 0 to P, P by B power 1 by n into dP. Okay. And for C, 0 to P, y dP equals to n into 0 to y, B y power n into dy. Okay. That these two equations over. So now du, what we got from here? Du equals to dy dy is P, or just differentiate u equals to that energy equation. So dy dy equals to P, and dy dP is 1 by n, P by B power 1 by n. Okay. So now P by B power 1 by n is what? That is equals to y. So 1 by n into y. Okay. This we got. Next, this is for strain energy. Right. Complementary energy. This is first complementary. So dC by dP is y, and dC by dy is equals to B and y to the power n. So right, B into y to the power n is what? P. So n into P. So now we have two equations in terms of this one. So first see, before seeing this one, just first see this equation. Okay, and in previous slide this equation. Right. Here what we will do, according to Castigliano theorem is valid for only the linear elastic, okay, property material, and in that case y will be equals to 1. So sorry, n equals to 1. So put here n equals to 1 or anywhere. So wherever equation is there, put n equals to 1. So after putting n equals to 1, what you will get? dy dP is equals to y. dy dy is P there. So wherever n is there. Here. So dC by dy is np. So putting n equals to 1, dC by dy is p, and dC by dP is 1. So after comparing all the four, what you will get? du by dy equals to dc by dy equals to p, and du by dp equals to dc by dp equals to y. So this is the Castigliano equation, right? For n equals to 1. Remember, general energy method, for that P equals to B y power n. In that, if n is 1, then that equation becomes the Castigliano theorem. And that's why Castigliano theorem is valid for only the linearly elastic material. Okay? So here is the reference that you can refer, that TSG Maxen book. I earlier also told you I am just following the Maxen book. So for reference, you can go for the Maxen book also. Okay. So this is the reference book. So if you have any doubt, you can just comment on the video, or you can contact me regarding your doubts. I will clarify that. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.